We have a new topic today, a new section. Still on vectors, cross product it's called. And this doesn't make sense yet, so I'm not going to go into it yet. But essentially what a cross product does is that you have two vectors, u and v, or a and b. I've switched over to a and b's for these ones because it seems like the homework likes a and b now instead of u and v, but it doesn't matter, darn thing. It's the same information. Anyway, if you want to find a cross product, this I can show you. Don't worry too much about this mess yet. Can you imagine that you've got a vector u, oh, I should say a, in 3D, and you got another vector down this way, call it b, make it even a little bit longer. Then the cross product called a cross b, that's how you say it out loud, a cross b, is a vector that has a very interesting property. It's this red vector here. And its very interesting property is that it is right angled to both of these vectors. So can you imagine these two pens were A and B? This green pen would be the cross product. So if I try and put them together, it's not going to work, is it? Oh, maybe do it the skinny side. Can you imagine in 3D, right? A and B. Can you see this green pen if I rotate at different angles? Can you see it's at right angles to these two guys? The cross product is unique except for direction and length. In other words, couldn't I do a vector twice as long as that would be the same property? And couldn't I vector pointing down the way that has the same property? And the cross product generates a vector that is at right angles to A and B, right, orthogonal. And I think it uses what's called the right-hand rule. So if you think of these two fingers as being your A and your B, the thumb is the cross product. And I think it's called the right-hand rule because the thumb is on your right-hand side. But it might be called the left-hand rule because I can never remember which one is which, in which case it's still the thumb. Why do you need those darn things? It's something to do with magnetism, or I think it's something to do with electricity and magnetism. So actually, it's also to do with torque. Anybody here know what torque is? Yeah. If you do the cross product, you get torque. Torque is the force that's screwing the bolt in or screwing the bolt out, you know? So you have a thing and you have a lever on it and then you have an angle and so on. So it's connected to torque as well. So the bottom line is a cross product is a vector that's perpendicular to A and B, and that this vector is unique except for length and direction, right? It's going to be the same vector essentially, but it might be longer or it might be pointing downwards. Well, before we get too caught up on what this thing is, I'm going to show you this skill. How do you find the determinant of a 2x2 matrix? Now, if I'm really lucky, some of you might even have heard of the determinant of a 2x2 matrix. Has anybody heard of that? No, don't matter. So, a 2x2 matrix. Well, let's start off with what a matrix is. A matrix is just a table of numbers, right? So here is a matrix. It's a 2x2, and that's because it has 2 rows and 2 columns. So there's row 1 and row 2. And you can imagine column 1 and column 2, right? So it's a 2x2 matrix. Now there's a thing called the determinant. Of a 2x2 matrix, and that's what we're going to get some practice at finding. The determinant of a 2x2 matrix is a number, right? It's a scalar, and you get it by, and it's normally written with this notation. Do you see it looks like the same matrix, but the little bends are taken off? It's two straight lines. It kind of looks like the absolute value thing, doesn't it? That symbol, two vertical lines. It's not, it just looks like it, right? It's just double duty. So how do you get it? You multiply these two together. And these two are called the major axis. And 2 times 5. Then you take away the other guy, and it's either called the major axis, it's also, oops, called the minor diagonal. So I'm giving you every name I can think of. Major axis, minus axis, major diagonal, minor diagonal. Basically, 2 times 5, take away 3 times 4. And what's that going to be? In this case, 10 take away 12, the answer is -2. So if I give you a 2 by 2 matrix, do you feel comfortable about how you would calculate what's called its determinant, right? Major take away minor. Let's do another one. 5, 0, 3, -1. Major, 5 times -1. Subtract, minor, 0 times 3, answer, -5. How about 10, -1, 2, 3. Major diagonal, 10 times 3. Subtract, minor diagonal, 2 times -1. 30, add 2, 32. Are we comfortable now about how to get this thing called the determinant of a 2 by 2 matrix? You feel good about that? Right, okay. So that's a little skill that we need. Why do we need it? Because it's going to get used over here. Now, again, before I go anywhere near there are 3 special vectors. Let's remind you who these 3 guys are. I haven't used them much because I like this component form, right? But you remember I, J, and K. Isn't I 1 in the X direction, J 1 in the Y direction, and K 1 in the Z direction, right? You remember those vector guys? Okay, so if you got an answer and it was 3I, take away 2J, plus 4K, I hope you're all comfortable that it's the same as this guy, right? So they're exactly the same information. This is IJK notation, and this is component form notation. A couple of reasons I like this notation. Isn't it less writing? And secondly, if any of these are 0, I could make a mistake. Whereas, well, let's put a 0, 1 in. Suppose it was 3I plus 2K. It'd be 3, 0, 2. Do you see in this notation, I can see that the Y component is 0. In this notation, isn't it easy just to miss the I and the J and the K and just say a 3 and a 2 and not notice which one is the 0 term, the term that's missing? That's a little side issue, but we're comfortable with that. Okay, so where are we off to next? Let's show you how this formula really gets done. If you go to textbooks, they will show you the formula for A cross B, right? The cross product of a vector A and the cross product of a vector B. And you're most likely to see it as this one. This combination I subtract this combination J plus this combination K. Now, if you had a great memory, I guess you could just memorize this formula and realize that A1, A2, and A3 are these numbers, and that B1, B2, and B3 are these numbers. But it's not that good, right? It's not going to help us with this type of calculation. So there is a way that pretty much everybody I know actually does calculate the cross product. And we're going to use this fella up here to do it. So let me show you how that works. We're now going to look at finding the determinant of a 3 by 3 matrix. This particular matrix. So let's suppose I want to find a cross product, and this guy is 1, 2, and 4. And the other vector is 3, -1, 1. How do I find the cross product? Well, I use this fella. So this is how you set it up. You put an I here, put a j here, and you put a k here. So your first row is always going to be I, j, k. The second row is going to have the components of A, and the third row is going to have the components of B. Are we happy about how you set up this table? Right, pretty straightforward, right? A's go in the middle, B goes in the bottom. Now, to get the determinant of this matrix, there's going to be 3 pieces. There's going to be an I component, a j component, and a k component, essentially what this is saying. But I'm not going to use these formulas. I'm going to use this. It's a little trick, but it works really well. I want to know the number that goes here, right? The I component. You cover up the I component. In fact, you can cover that up as well. Do you see a little 2 by 2 matrix now? And you find the determinant of that 2 by 2 matrix. So let's go. 2, take away -4, right? 2 times 1 is 2, subtract -4, 2 add 4 is 6. Are you happy about where the 6 came from? Right. Now, that's how you got the I component. Shift it along. And now do the j component. See I'm covering up the j? Do you see another different, slightly different, 2 by 2 matrix? And major diagonal is 1, right? 1 take away 12 is -11. And then finally, you do the k. Do you see yet another 2 by 2 matrix? And -1 take away 6 is -7. Now, that's how you get the I, the j, and the k. Do you notice that there's and it's part of the formula, and there's a reason for it, you just have to trust it. Do you notice that the middle one is always a negative of the j? See that negative? Right, so I'm ready. I got the answer. 6 of these. -11 gets you +11 of those, and -7 of those. I have now got my cross product. Now, according to what I said at the start, if you can imagine this as being A and this is B, then shouldn't the cross product, this guy, shouldn't he be perpendicular to A and at the same time perpendicular to B? Right now, you're just trusting me that this actually works, that it does give you what we said it does. So let me check it. If I do a dot product with these 2 vectors, right? A dot product with this, I get 1, 2, 4, dot product with this guy, 6, 11, -7. Okay, 1 times 6 plus 2 times 11 plus 4 times -7. What does that get me? 6. Add 22, take a 28. Am I good or am I good? Doesn't that mean that they are right angles to each other? So this piece of magic, this weird formula that you're just told exists, nobody tried to prove it. It's very difficult to prove why it works, but it works, right? Now allows us to find a vector orthogonal, right? Perpendicular to A and B. I won't do the other one, but can you trust me that the other one also works? Right? If I did B dot A cross B, I'd get 0, which means it's right angled. And this technique doesn't use ugly formula. Isn't it kind of a visual technique, like a kind of cover up? So it's always a good idea, if you see something, to see another example, right? Because 2 examples are better than 1. And I'm going to pick a version of question 4. And here the vector A is called 4, 5, and 0. And the vector B is called 1, 0, and 7. And we are going to find the cross product, right? Well, let's find out. I go I go J, I go K. Great, that's the start. A goes first, so 4, 5, 0. B goes second. This is basically a 3 by 3 matrix, and what we've been doing here is calculating its determinant. So if you're wondering the connection, that's where it is. So many I's, take away so many J's, plus so many K's. You remember the minus fella. Right, let's try each one and see how it goes. You want the I component. There, you see your little 2 by 2? What would you get? 35 take away nothing, right? Major take away minor. 35 take away nothing is still 35. If you do the one in the middle, it's a bit hard to hide that. Can you just pretend it's not there, the top row? 28 take away nothing. Oh, 28. Last one. Ooh. Major diagonal is 0, right? 4 times 0 is 0. Take away 5 gives me -5. And our answer then is 35, the negative of this, so -28, -5, and we are finished. It's magic, right? You're doing it because it works, but do you like it? Is it something that is doable and you could remember how to do it? Right. So if you know how to do that, you know how to do cross products, essentially. So what we're going to do is practice at finding them, which hopefully will be pretty good. And then later on, what you can do with cross products that is quite interesting. Because if all they did was tell you a vector that's orthogonal to 2 others, it'd be kind of interesting, but you know, you'd lose interest in it, because if that's all it did, yeah, big deal, right? But let's move on. But there are other things it does. There are other properties of it that are very strange and very useful. But that's to come later. Okay. Now, some things can happen when you do a cross product. Most of the time, you just get some numbers. But sometimes, just sometimes, the cross product ends up being the 0 vector. Now, it's kind of hard to imagine that, but can you trust me, it could happen. What do you think is the connection between the A and the B vectors if the dot product is 0? What property do you think they have?
Are they also perpendicular to each other?
That would be interesting because, yeah, I think I see your brain. It's not that, but that's kind of interesting. Yeah. Good thought process. But oh. Any other ideas?
If 1 is the 0.
Oh God, yes, never thought of that. Yeah. If either of them is a 0 vector, you're going to get 0 as the answer, which is true. Can we pretend that 0 vectors don't exist for this section? Because none of them are 0 vectors, but technically that is exactly correct. Okay, here's the guy. Do you know if the two vectors are parallel? Their cross product will be 0. So that means I now have a very quick check. Are these two vectors parallel is the question, yes or no? Couldn't I do the cross product? If the cross product is 0, 0, 0, they are parallel. If the cross product has any kind of numbers in it, they are not parallel. Okay, so there's a little use for cross products. Now, if I find the cross product A and B, and it ends up being this 35, negative 28, negative 5, what do you think I would have got if I'd switched places with A and B? And this is really just gut feeling, and there's no reason you should know this, but what do you think might be true?
Would it be the negative?
Whoa. Where did that come from? Because it is correct. Was it just a gut feeling that would be?
Well, since we're subtracting the major to the minor, and then we're kind of flipping it, then it's just a negative version, right? So.
Very good, yes. So this is a general truism that, I guess I should write it the other way around, that B cross A is the negative of A cross B. Are we good? Any questions so far? Okay, looks good. So if I was doing my notes for A cross B, technically, this is the formula that you'll see in many textbooks. But have you noticed I haven't even written this formula? Haven't I done it totally visually? Right. And I strongly suggest that unless you're one of those brains who just love formula and you know how to use them and you're great at memorizing them, it's probably not a good idea to try and even use the formula. Virtually nobody I know actually does use the formula. We tend to use this visual technique. Same answer, I think, just easy. Okay, so nothing much happening here. Right, nothing here. Oh, okay. This is an example of something like question 7. A is going to be I, take away J, take away K, and B is going to be 1/5 I, take away 2/5 J, plus 3/5 K. And pretty much the standard question, right? Find A cross B. Well, we have an I, we have a J, and we have a K. And it's 1, negative 1, negative 1. Are we all comfortable about what A looks like? And B is 1/5, -2/5, 3/5. In fact, this notation works really well with this, doesn't it? It's quite easy to transfer this to here and this to here. Okay, so many i's, subtract so many j's, pardon me, plus so many k's. Cover the darn thing up. See what we get. -3/5, right? -3/5, take away +2/5. So take away 2/5 in other words. So -3/5, take away 2/5 is -5/5, -1. Excuse me. 3/5, take away negative is like adding it, so hopefully that's 4/5. -2/5, add a fifth is -1/5. And we end up with, I believe, -1, -4/5, -1/5. Are we comfortable about finding cross products when they use IJK instead of component form for the information? Of course, you know I can't count, so if any of these are wrong, you want to tell us now, and I'll double check.
Is the last one -3/5, or am I doing it wrong?
It's -2/5. Take away a negative means you add it. So -2/5, add 1/5. This particular time, I think I'm correct, but it's worth checking. So it's -2/5
Oh, yeah, you're
plus, right? You've got these negatives and subtraction things going on, so sometimes things end up being plus because of that. I'm getting a pretty good vibe of cross products. If I give you two vectors A and B and I say, find A cross B, you're comfortable with doing that. Right. Now, a lot of these questions have a part B where they ask you to verify or check your answer. And it'll typically be written something like this. Not a cross, that's a dot product, sorry. And won't the answer be 0? Are we okay with that? If you do it correctly, won't the answer be 0? And if you do it wrong, won't the answer be some other number that's not 0? So really, that's just a check. So if you're 100% sure that you're right, can't you just say 0, 0 and save yourself some work? In a test, I would definitely do that check in case something should have been -1/5 and not +2/5, right? Me personally, as you have no doubt found out, can be very careless, and so I have to be extra. Having checks is helpful, but not doing it 10 times in a row, right? That probably gets a bit pointless. So I'm just saying, when you're doing the second part of a lot of these questions where they ask you to do this, if you're really sure that you've done it right, 0 and 0 is what you're going to get. So let me give you what is a bit of a strange question. Here is a vector 1, 2, -3. B is going to be the vector -1, -1, 2. And C is going to be the vector 3, 2, 0. And we're going to look at calculations involving cross products and 3 vectors, A, B, and C. Technically, there's only really 2 situations that make sense, right? First situation is you could be asked to find this fella. Or it could have been written down this way. Would you agree that that's the same thing, right? Because in dot products, now this is dot products. In dot products, does it matter who's first, dot who's second? No, right? So this to me is the same question. So what we've been asked to do is find the cross product of A and B, and then whatever that answer is, do a dot product with C. When you see this particular calculation, it is called, very often, it's called a triple product. And right now we're just calculating it. But a triple product is fascinating what it gives you. First, will the final answer to this be a vector or a scalar? Will it be a vector or a number on its own?
Scalar.
Scalar.
Be a scalar. And I'm going to cheat a little bit here. What on earth does this number give you? Right, the cross product of A and B dot product with C. You wouldn't, well, I wouldn't guess this in a million years. I want you to imagine that this is vector A, and this is vector B, and this little guy here, I'll point him down the way, is vector C. If you find this triple product, you find the volume of that three-dimensional shape. It's equivalent to a three-dimensional parallelogram. If it looks a bit like a cuboid, it's because I haven't really made it extreme enough. But in general, it's a three-dimensional parallelogram. And it has a lovely name. I love the name that they give to this. What you're going to find is the volume of a, wait for it, parallelepiped. It's called a parallelepiped. Oh, come on, is that not a cool name for something? Isn't that the name of, that should have been the name of a pixie or an elf. And here's my elf friend, parallelepiped. Okay, none of you have the same vividness. Okay, let's put somebody in a spot. I'm not meant to do this, but it's fun. Sam, I'm picking on you because you're my go-to pick-on person, right? Say that word.
Parallelepiped.
Oh, darn it, you said it right. Douglas, go for it.
Parallelepiped.
Okay, Kathy, I'm picking on you. You ready? Wait for it. Say it 3 times very quickly.
Oh, that's just rude.
It is just bad, isn't it? You want to go for it?
Sure.
Go.
Parallelepiped, parallelepiped, parallelepiped.
Oh, God, everybody's doing it right. Well done. Yes. I just don't know what it is about that word. It just strikes me as being such a pretty word. Who knows why? But back to this. I now know how to get the volume of that. Can you imagine how hard it would be to try and calculate the volume of a 3-dimensional parallelogram, right? That's essential. It's like a box that somebody sat on and pushed out you whack. Very cool. Well, let's do it now. Triple product of A, B, and C. So I guess I need to figure out what's the best order. I think the best order would be to take care of the cross product first, because that's the one that we're most comfortable with. So it's going to be I, J, and K. And it's going to be the vector A, so 1, 2, and -3. And the vector B is -1, -1, 2. Okay. So we're going to get so many I's, take away so many J's, plus so many K's. And if I cover this guy up, we get 4 take away 3, which is 1. If I cover up the middle one, we get 2 take away 3, which is -1. And if we cover the last one up, we get -1 take away -2, which is add 1. And I did not expect that, but it's kind of interesting that this is what we got. 1, 1, 1. Unless I've done some mistake, does that look good? That the cross product in this particular case is a vector 1, 1, 1. Okay, now dot product with it. So cross product dot C is going to be 1, 1, 1 dot 3, 2, 0. And in this case, you get 1 times 3 plus 1 times 2 plus 1 times 0. And the answer I get is 5. So far, so good. So the volume of this is 5 cubic units, whatever the units happen to be in. Now, there is a little hiccup, just a little. Sometimes the triple product is a negative number. So if you imagine a totally different question, right, with different A's, B's, and C's, and we did everything, but we got -10. The triple product technically is -10, but what is the volume?
10.
It's 10. So if you stick an absolute value around it, you get the answer. But normally I just do the triple product. If the answer is 5, it's 5. If the answer is -10, I know that this is representing a physical volume in 3D, right? It has to be a positive number. And so I do it. So I'm quite careless about the absolute values. Another reason I don't like the absolute values, because that's what these are, doesn't it also look like the magnitude symbol? And so what people end up doing is finding magnitudes of vectors all over the place, and they screw up the question. So if you don't have it, you're less likely to do it. And then you just remember, if the answer is -2, it's really 2. And that way it avoids confusion, right? Because we're using this absolute value. Actually, we're using it in 3 ways. You know, the 2 vertical lines? Here's the 3 ways. Absolute value, magnitude of vector, and determinant of 3 by 3 vector. Do you see it's the same vertical 2 lines having 3 distinctly different meanings, what they do. So I'm trying to sell the fact that I don't put these down. Are you comfortable with why I don't put them down? If you like, they're there, but you just don't write them. Saves confusion. Now this, again, it's gut feeling. There's no reason you should know this. But let's suppose that you did a triple product and the answer is 0. Geometrically, how could that happen? And we'll avoid the A, B, and C could be zeros, because that's true. It is. But what other normal 3 vectors, right? Normal vectors, right, with numbers everywhere. How could that happen? Because it can.
Would it be if
Could
it
be a
was
plane.
like a cube?
Oh, like they were all right angles everywhere? Yeah. I understand why, but no, but that's a good thought. Good thought process. Nothing wrong with that idea. It's not the reason. How could you get 0 volume from 3 vectors? I guess that's the problem.
There's no height.
2 of the vectors are the same.
Oh, that would also work. A and B could be the same vector. That would screw it up. Yes, that is true. There's one other way that's more typical, but what you said, Kathy, is correct. If A and B were Parallel even would be enough. Don't even need to be the same. Last chance? Okay. Can you imagine A, B, and C all being on the same flat piece of paper? So someone mentioned something like there was no height. I think I caught that. That would be the equivalent of no height. Can you imagine A, B making a plane and C is just a vector in that plane? Now, when this happens, when you have three vectors all on the same piece of paper, now it doesn't need to be flat. Can you imagine it could be bent like that? It's still the same piece of paper, right? It's still a plane. And when that happens, we use the word coplanar. I believe there's a homework question where they give you three vectors and they say, is it coplanar? And the answer is yes, it is, or no, it's not. Will you not do the, I'll hit yes, and if it says it's wrong, I'll hit no, and that way I don't need to think about it. Right? Will you actually find the triple product? If it is 0, it's coplanar. And if it's any other number, it's not coplanar. Are we cool about that one? Right. So you could get a cross product and then two vectors cross product with a dot. Have you any idea what the other combination of cross products and three vectors might look like? It's going to have that guy in it. What could I do with the third vector C? Last chance, any ideas? That one. As far as I know, that doesn't have a name, right? The other combination is called a triple product, right? But you can also get A cross B cross C. Now you might think that that's probably just going to be a zero vector, you know. How can you have a vector at right angles to two vectors and then at right angles to another one and all be true at the same time? But actually it does exist. Now, since I've already done half this question, haven't we already found A cross B, which is 1, 1, 1? And let's do a cross with C, which is 3, 2, and 0. Can we do that just to save some time, right? Because I've already done the A cross B part. Now, in our A cross B cross C world, it's going to have an I, a J, and a K. 1, 1, 1, 3, 2, 0. So many I's, take away so many J's, plus so many K's. Agreed? Right, let's see what we get. All my usual covering up things going on here. 0, I should say, take away 2 is -2. 0 take away 3 is -3. And 2 take away 3 is -1. And this fella is -2, +3, -1. And we have found A cross B cross C. This vector doesn't have any particular interesting uses, right? But it exists. Technically speaking then, if I had 5 vectors, couldn't I do A cross B cross C cross D cross E and get a vector? I don't think geometrically it would have any particular significance, right? It wouldn't mean anything very useful, but it's doable, right? And for the last few moments then, I've done A cross B, which is this fella, right? If I find the magnitude of A cross B, which in this case is what? 1 squared plus 1 squared plus 1 squared, which is the square root of 3. So I'm using this as the magnitude version, right? Because it's a vector inside it. You might think, what does this number look like? If this is A and this is B, the magnitude of the cross product is the area of the parallelogram. Now that's not intuitive, is it? I mean, that doesn't seem obvious. How should the magnitude of a cross product tell me the area of this parallelogram? Now, bear in mind, this has to be positive, right? Because it's a physical area, right? But if you're finding the magnitude of a vector, isn't it guaranteed to be positive, so you don't need to worry about signs? Now, what would half the magnitude of a cross product get me?
Area of the triangle.
Correct. So if you imagine a line going down here, it gives you the area of the triangle. So do you see that if I have two vectors, just two vectors in 3D space, doesn't the cross product tell me all sorts of things, right? The cross product tells me a vector that would be perpendicular to the two. But the magnitude of that cross product would be the area of this parallelogram, and half of that would be the area of this triangle. And if the cross product is 0, which we talked about earlier, doesn't that typically mean that the two vectors are parallel? Right? In all of these, we will assume that A and B are not 0 vectors, right? Because if A and B are 0 vectors, everything's 0, no matter what you do, right? Am I selling you that the cross product is somehow useful to find? Not just because it tells you a vector perpendicular to two others, but because of some of the other things it tells us. And then when you combine it with a third vector and do a triple product, isn't it even more interesting what it gives you? It gives you the volume of a parallelepiped. Or if that number is 0, it tells you that A, B, and C are coplanar. We learned some cool stuff today. Say hi.